Okay, now Jeff, who can actually draw, I can't, has done this little diagram for us that we're going to use to explain the light-dependent reactions. Now, as you see here, this is a little diagram of the chloroplast, and what we've got here are stacks of membranes, the thylakoid membranes, and these stacks tend to be called grana. And here's a cutaway of the thylakoid membrane here for us to actually describe how light energy is trapped, and then how those two temporary energy stores, ATP and NADPH, are produced as the outputs, okay? So what actually happens is, now we're going to have to start adding things. The chloroplasts are amazing organelles in that within the membrane, embedded in the membrane, are protein complexes which actually will trap the light and then transfer energy down through the membrane. So they're about 40% protein, which is quite a lot. And it's this whole business of that membranes can actually keep things out, keep things in on one side, that actually help them to be like little factories and making things happen. So first of all, imagine it's a sunny day and the sun's shining on those thousands of little chloroplasts within the cells, those little green chloroplasts. The light shines and it's trapped within the chloroplast on a special molecule called chlorophyll, which is in a special complex. Now, I need to call on my artist here to start to put things up for me. You're going to draw some things, aren't you, Jeff? Yeah. Good on you, come on. So, let's see, within the membrane, and again, this is just a cutaway of it, you would have a special complex where light is trapped. So, can you remember what the complex it would be? Up in here would be the chlorophyll, the photosystem 2 it's called. Okay, so just do a square for it would be good, like a blue square. And it's just, photosystem 2 is a complex of what they call light harvesting complex, and it harvests the light energy and funnels it so that it actually ends up getting captured by a chlorophyll molecule. And I think actually in the book it might be like a diamond, Jeff. But photosystem 2, it actually runs on the special wavelength. It's called P680, right? And what does that mean is the wavelength of light that actually activates it is 680 nanometers, the size of it. And attached to this as well, maybe if I get a blue, green, whatever, yep, we have another complex, and it's called the oxygen evolving complex, or the OEC. Maybe to save us putting an acronym, I'll actually call it the oxygen evolving complex. And it is associated with photosystem 2. And as we'll see, what it actually does is it will release oxygen, but another thing it releases, are when it splits the water, actually called photolysis, is hydrogens and electrons, which are really important. Now, within this chlorophyll, this photosystem 2 complex, there is a chlorophyll molecule. Now, these molecules are special. They actually have a magnesium in the center of them, and that magnesium in this special, what's called a porphyrin ring, can actually lose electrons, okay? And it gets excited by a specific wavelength of light in 680 nanometer region. All the other light sort of funnel down to it. And it's almost like, imagine the analogy, Goldilocks and the Three Bears. You know, if light energy is too strong, that electron will be lost. It'll just jump out of where it is and get lost. If it's not strong enough, it'll jump up to a higher energy level and then drop back down again. So it's like the porridge, it has to be just right. That's why 680 is just right, okay? Now what happens to that electron is it actually then starts to be passed down what's called an electron transport chain, okay? And it goes from one complex, and again, we don't need to know what these complexes are. The key thing is the electron, which is lost from the chlorophyll, is transferred from one complex to another, and each one's at a lower energy level, so it's almost like analogous to, imagine a ball bouncing down steps. The ball's got high energy at the top of the step, and it starts to lose energy as it drops. This is what's happened to this electron. Now the key about it going down this electron transport chain in the membrane is that it actually does work. Some of these complexes will pump hydrogen, this is a key thing, across the membrane, and hydrogens start to build up. Okay? The other thing, there's another reaction here where the water is being split by this oxygen evolving complex being driven by light as well. So it's another way of creating hydrogens and electrons. You've got hydrogens, electrons, and then the oxygen, which is given off. So you get hydrogen being pumped across. As each of the chlorophylls loses an electron, it gains another one. So it's a continuous process which jumps back onto the chlorophyll and then is lost again by more light energy. So it's like a continuous process. Oxidation means what? You lose an electron, oxidation, and you gain electron reduction, as we described in Unit 2. So this is oxidation reduction process that's happening to create this, what actually ends up being like a hydrodam building up here. See all the hydrogens on this side of the membrane? There's hardly any here. There's loads of hydrogens here, which actually bring the pH down as well, so it becomes really acidic in here. And this is lots of energy in this membrane, the inner thylakoid membrane, okay? Now, let's just talk about producing, this energy here is actually going to be harnessed, okay? And what it needs to harness it is a special complex within the membrane, and actually this is actually what it looks like. It's called, this enzyme is embedded in the membrane, and it's called an ATP, you see the name gives it away, ATP synthase complex. Okay, so you're saying, okay, it's going to make ATP. So what it does is it uses the hydrogens that funnel through this special complex, and what you get then, the energy from the force that these hydrogens coming through produce will actually give you ADP, here's our input, will become ATP, which is the output. So that energy of the hydrogens building up here will create ATP, okay? And they actually call, because hydrogens are called protons, you know, the ions, they call it proton motive force or chemiosmotic theory and stuff like that. But basically, hydrogen built up here, like a hydrodam. Imagine analogous to water going through or whatever, creating energy, and you get ATP coming out. So the hydrogens drive this reaction to create ATP. All right, so that's one of the outputs. Now the other, yes, sorry, Joe?
Just.
Oh yes, thank you, Jeff. And somehow it drives that. And they still don't know how it works, but it's an amazing, yep, and it comes back all the way out into this thing again. Now, that's one of the outputs. The other one from the light-dependent reactions is NADPH. And what we have here is there's another complex called photosystem 1, would you believe? The reason they're called photosystem 1 and 2 in that order is that photosystem 1 was discovered, the one I'm going to put up here, discovered first, and then photosystem 2 was discovered second. But again, it's another range of molecules in here, and there's another chlorophyll molecule here. Now this one, this complex is called the P700. And remember I said here we got 680 nanometers is the one that's just right, the wavelength is just right. Well, guess what? This is a slightly longer wavelength, less energy, is what's just right for this one. And again, an electron will then travel down through other complexes here. Again, we don't need to know the names, but the electron transfers down, losing energy all the time. And what it does at the end is it creates NADP plus the hydrogen. That energy, it reduces that to NADPH. There's an enzyme, NADPH reductase, which will actually produce this. So again, it's another series of oxidation reduction reactions, then ends up with reduction of NADP plus a hydrogen to NADPH. And again, these two are the outputs, as we'll see over here, the outputs for the light-dependent reactions. And as I said earlier, what you've done is you've taken light energy and you've actually turned it into temporary energy stores here, which then, these outputs then become the inputs for the light-independent reactions where carbon dioxide is fixed. And the other thing that happens, the water is split, which is an amazing reaction. If we could actually split water without having to expend more energy, if it was free to split it, we'd have oxygen and hydrogen, which are amazing energy sources, very clean sources of energy. We can do it, but it costs more energy than it actually gets out, in terms of inputs, outputs. So The oxygen, as I said, is important. It goes out, it's a byproduct into the reaction. And the hydrogens and electrons are used to drive the process. So there you go, oxygen as an output as well of the light-dependent reactions.